Hello to everybody. So we are back with exercises on power series. I recall you what is the ratio of our exercises on power series. So we have series like this, an, xn, and going from 0 from 1, it's not very important, to plus infinity. And an is real, and the question is, main question is finding the radius of convergence. First question. And the second is the interval of convergence. Okay, these two questions are the usual ones, and what I propose you as an exercise today is this sum of n x to the power n factorial. Okay, so the first question is whether this is a power series or not. The answer is obviously yes, because this is x to the 0 factorial, which is 1. So this is for n equal to 0, plus x to 1 factorial, which is again 1. So this is the term related to n equal to 1, then plus x. So it is 2 factorial, which is 2. 3 factorial is 6. Then there is plus 24x to the 24, x to the 120. So these are powers of x. So this is a power series. Of course, there are missing terms. X to the cube is missing, x to the 8th power is missing, and so on and so on. Most power, so to say, most power are missing. But this, in terms of our generic writing of a series like an x to the n, means that most of the coefficients an are 0. So nothing special. But what is special here is how to study the radius of convergence. Why? Let me be a bit, as usual, pedantic and boring on that. So here we have a0 is equal to 1, a1 is equal to 1, a2 is equal to 1. Then we have that a3, a4, and a5 are equal to 0. Then a6, coefficient of the 6th power term, is equal to 1. And then from a7 up to a23, they are all equal to 0. So if you want to apply the ratio criterion that tells you that R is equal, whenever it exists, to the limit for n going to plus infinity of an divided an plus 1, most of the time here you find zeros over 0. So here you don't have a limit. So in this form, the ratio criterion cannot be applied. And even the root criterion cannot be applied. So if you have the power 1 over n, so the nth root of an, so here you don't have a limit because most ans are zeros. So there are some subsequences on which this sequence is constantly 0. In other subsequences, it is equal to 1. If you take an factorial, you always find 1. So for people who depend a bit here, what is the more profound view of this argument, of course, even when the limit does not exist, you can compute something which is called the lim sup. I don't want, and the limit, but I don't want to stress this fact. Okay? So forget about the usual criteria and go to this series and try to work on it directly. First of all, it is easy to observe that if x is in absolute value larger than 1, then this series cannot converge. Why? Because here we have something larger than 1. Here we have the same thing. Then we have something larger than 1 to the square, then to the 6th power, and so on and so on and so on. Then it goes to plus infinity. So if x is larger than 1, then the series diverges. Moreover, if x is strictly less than 1, this is nice to see what happens. It happens that here we have x plus x again, so 2x, we start with 2x. Then we have x squared that we can replace with modulus of x to the 2nd power because it is a square. So if there is a minus, then it becomes a plus. Here there is, less than minus 1, not less than 1, less than minus 1. Okay. Then we go to x to the 6, which is equal to modulus of x to the 6th power. So from the 3rd term on, we always have an even power, so we have positive terms. So this goes to plus infinity. So as a conclusion, when the modulus of x is larger than 1, then the series positively diverges. Okay. Now, let us look at what happens when modulus of x is less than 1. So here we have modulus of x larger than 1, then the series positively diverges. Then for modulus of x less than 1, notice that the series we are studying is estimated from above by, in modulus, is estimated from above by the geometric series with the same x. So I write it. We have that x to the n factorial in modulus, which is nothing but the sum of modulus of x to the n factorial. This is less than the sum of modulus of x to the n. Why? Because the only difference from these two expressions is that here, in the 2nd expression, we have more terms. We have more powers. And all terms we have here are positive. So this is strictly less. But now, x has been taken less than 1. So this series here is convergent. So this converges by comparison. There are a series of positive terms because we took the absolute values. So we have that the original series absolutely converges, then it converges. If a series, a numerical series, absolutely converges, then it converges. The vice versa is not true. Okay. But if we have convergence of the series of the moduli, then we have a convergence of the series. Then here, we have that our original series converges. X larger than 1, we have divergence. For modulus of x smaller than 1, we had convergence. So we found R, the radius of convergence, which must be equal to 1, without using criteria, without doing the usual computation. So okay, let me insist on this. We have 0 and we have -1 and +1. So here and here we have that the series diverges. Here inside we have convergence. Therefore, the conclusion is that the radius of convergence is equal to 1. So without the possibility of using ratio criteria and root criteria, what we had to do was to look at the series directly, to look at it straight in the eye and try to see what happens. And we found the radius of convergence. But what we did up to now does not affect the extreme points of the interval of convergence, +1 and -1. What happens there? As usual, we have to check them directly. So we have to check sum n from 0 to +infinity, 1 to the power n factorial. So we have 1 + 1 plus log +1. This is equal to +infinity, an infinite sum of ones. It is completely harmless, the fact that there are some missing powers here and there. Power 7 is missing, power 9 is missing, power 14 is missing. When you write down the series, this is just an infinite sum of ones. So it goes to +infinity. And what about the sum of -1s? So, sorry, not the sum of -1s, but just the series computed at x equal to -1. So here we have 1 plus 1, sorry, plus -1 is n equal to 0, n equal to 1. Then we go to n equal to 2 and we have plus -1 to the second power, so +1. Then we have -1 to the sixth power, so +1, and so on and so on. So except the two first term, in particular, affect the term with n equal to 1, we end up again with a sum of infinitely many ones. Why? Because the power is always even. When you are computing the factorials are all even except one factorial. So you end up with +infinity again. Therefore, there is no convergence in -1 nor in +1. So the interval of convergence is the open interval -1, 1. Okay? And this is all for this first exercise. And the message of this exercise, sometimes you could be given strange series like this, where it is not possible to apply it in a straightforward manner the usual criteria, root and ratio. Message, put your hands into the series and try to understand what happens. Okay, last exercise of power series, then we will move to another topic of the course. So consider this series. You have sum for n equal, okay, from 0. Yeah, from 0 up to infinity of 2 x minus 1/3, everything here to the nth power, and here you have 3 to the n times n plus 1. Okay? So it can be given like that. Immediately, you must observe that it is not of the type x to the n. It is a power series because there is x to the n, but it is not really x, it is x minus 1/3. So it is not centered at 0. It is centered to another point, which is 1/3. So it is not a Maclaurin series, so to say. It is a Taylor series. It's a genuine Taylor series, but nothing dramatic. This 2, which is inside the parentheses, can be taken outside. So let me write it again in this way. This is 2 to the n x minus 1/3 to the n. Okay, and now here you can do as you want. You can just, for instance, consider a new variable y is equal to x minus 1/3. And in this way, you can rewrite this series like that. 2 to the n, y to the n. And this is the usual form you are confident with. So this, the role of this change of variable is mainly psychological. You are used to deal with series written in this form, so you keep on doing that. Nothing really serious. And now you can go to study the, as usual, the radius of convergence. When you have power, perhaps a good way is to use root criterion. Why not? So remember that R2 minus 1 is the limit for n going to plus infinity of 2 to the n over 3 to the n, 1 over n plus 1 to the power 1 over n, provided this limit exists. Okay, this is a simplified computation for the radius of convergence. Provided that this limit exists, this is the inverse of the radius of convergence. And so, of course, 2/3 can be gathered outside the sign of limit, and then we have the limit. I will not write again n goes to plus infinity because it cannot be different from that. So we have 1 over n plus 1 to the power 1 over n. So remember what I told you at the very first lecture of this series of videos. And when you have a polynomial in n here, the limit of the polynomial to the power 1 over n is always 1, regardless of the fact that the polynomial is a numerator, is a denominator, and regardless of the degree of the polynomial. 1 over n, the power 1 over n is stronger, is insensitive to these details of the polynomial. If the growth here is polynomial, or the inverse of a polynomial, the limit is always 1. Put it in another way, polynomial coefficient have not a sufficient strength in order to change, to move the radius of convergence from 1. So this guy is equal to 1. So R, the inverse of R is 2 over 3, so R is 3 over 2. Okay? And now one goes to see what happens at the extremes. So right here R is 3 over 2. And then we have to study what happens at the extremes of the interval, for instance, in y. If y is equal to 3 over 2. So this means having here 3 over 2 to the n, of course it cancels this guy here. So this is some n from 0 to infinity of 1 over n plus 1, and this is like the harmonic series. This is not like, this is exactly the harmonic series. So it goes to plus infinity in divergence. On the other hand, if y is equal to minus 3 over 2, so the series becomes as before, 3 over 2 to the n cancel this 2/3 to the nth power, so we end up with minus 1 to the n divided by n plus 1, and this converges by Leibniz. I repeat you what Leibniz asks, Leibniz criterion. First, alternate sign, one positive, one negative, one positive, one negative. Second, the generic term goes to 0. Third, the absolute value of the generic term is monotonically decreasing. So this is these conditions are all fulfilled here, so we have then this converge. Then we have that the interval of convergence for y is minus 3 over 2 plus 3 over 2. So let us go back to the original variable, which is x. And in the original variable, what you have is that x minus 1/3 equal to this extreme is equal to minus 3 over 2. This means that x is equal to minus 3 halves plus 1/3. This is a difficult computation. So you have 6, then here you have minus 9 plus 2. Is it correct? So you have minus 7 over 6. Oh, sorry, this was open. This was open. Our computation. So, on the other hand, x minus 1/3 is equal to the second extreme. Here you have x equal to plus 3 over 2 plus 1/3. And so again, here you have 9 plus 2, and here you have 11. Is it true? 9 plus 2 seems to be 11 over 6. Okay, the width is always 3. Good. So, finally, I write the result. I have to cancel to write down the final result. So x, the interval of convergence in the variable x is minus 7, 6, 11, 6. Okay, this is the interval of convergence. So, and this is all for this video and all for power series. And now we go to Fourier series. See you in some minutes.